It's a pleasure for me even to introduce Carlo Rubbia, because we have worked together for many, many years. I think we can even say we are some friends. So, what?
Half a century.
Half a century? No. Okay, so everyone knows Carlo Rubbia, so I can be brief on that. He got his PhD from Columbia, and since '61 he worked at CERN. But to tell you at the beginning, he has different time intervals where he does different work. So I know mainly the work from CERN. 1976, he suggested to transform the SPS into a P-by-P collider. And that was something new at that time, and it needed something, namely an antiproton factory, because the magnets are the same and the particles go in one direction and the other. Fortunately, there was also Simon van der Meer there, who was able to build, together with Carlo and others, to build a P-by-P factory. Look at the times compared with nowadays. This was 76 where he suggested. 81, we had the start of the P-by-P collider, so 5 years later. It's very fast. And 83, we had the discovery of W and Z. And many people, I worked with Carlo on UL1. He was a big boss, and that was good and bad on certain things, but he did one thing: he made it fast. So whatever we had to build and so on, if it doesn't work, he put a lot of emphasis. And I found myself very often in the situation, I said, my God, if I would have been on Carlo's place, I would never succeed. So you need a certain strength to get such an experiment through in that time. Now, very often people told me, yes, that's easy, we know where the W and Z is, and so on. It's not, because the main problem is the background, and the background is very difficult to understand, and we did not understand it at the beginning. Now, the discovery of W and Z was 1983. 94, he got the Nobel Prize, and our group at that time was 100 person, UA1. There was a second experiment, which also found W and Z, which is UA2. Now, from then on, it goes more or less automatically. I also should mention something which is important. During the whole time, 1972 to 89, he was a professor at Harvard, Higgins professor at Harvard, which doesn't make life easier, because most of the time when he came to us, he was jet-like, which is not always an advantage, but he really had a hard time. Now, besides that, in that term, he had another occupation later on, that was 89 to 94, because he became the CERN DG. And I think for me it was a big release, because at least there was a CERN DG, which is not often the case, who understands the things, and compared to some others. Then he changed completely, because this little CERN is not enough for him. So he went into different things, and in 1990, or a little bit later, he suggested an energy amplifier. I cannot go in detail, but it's a safe way to produce more or less an unlimited nuclear energy. And the safe is a very important part on it. Why is it so safe? Because he used accelerator technology. So switch off the accelerator, the thing is off. So that, I think, was a very important part. And more and more he went also in the kind of technologies for environment and so on, which is very important. Now, I have to be fast, so 1999 to 2005, he was president of ENEA, Italian Agents for New Technology and Environment and so on. All that goes almost parallel with the data analysis, but almost finished. Then 2007 to 2015, he was scientific director in the environment studies in Potsdam, Berlin. in Germany. I was very eager to see how he come along with the Germans. I mean, I know how he comes along with me, but the Germans in Potsdam are really also a little bit tough. I can tell you that is not so clear. So then he still didn't have enough. So 2013, I think it's a very important role, he became senator for life appointment for the rest of her life. Look for a job which you have the whole life, yeah. And that was given by the Italian president. And there he still has a lot of influence, which is important in my opinion. Don't think that he gave up physics, not at all. All that is anyway physics, but he is also a professor in Gran Sasso, and he had endless honorary degrees. One of them is the French officer de la Légion d'honneur. I'm living in France, so I know it's a very high title, and he has more with Polish and so on. So please welcome with me Professor Carlo Rubbia.
Thank you, Captain. You took 7 minutes of my time.
None of your talk. Five.
7 minutes, okay.
5 were mine.
Okay, very good. Thank you very much, ladies and gentlemen. It's a pleasure for me to be here today. I will try to cover a few questions related essentially to the particle accelerators, since there are so many other theoretical people which know better than me the answer to these different questions. The concept of a particle accelerator, the history of particle accelerator had probably its origin around 1930, when at the Cavendish laboratory in Cambridge and also in Germany. In a speech to the Royal Society in 1927, Rutherford expressed publicly the interest for the scientific community to accelerate charged particles to energies greater than those of natural alpha decays in order to disintegrate nuclei with high energies. You can see here the picture of the small NESO laboratory in which Sir Ernest Rutherford was working at the time. The cyclotron was conceived in Germany. Normal to a uniform magnetic field dipole, the frequency of a non-relativistic charged ion does not depend on the radius, since the greater distances are compensated by the increased velocity of the ions. The first 4-inch cyclotron has been constructed by Lawrence in Berkeley and operated in 1932 with his then student Livingston. The Betatron, based on a single accelerated magnetic field, was developed also in Germany, but first built in the US with Kirst in 1940. Both bending and acceleration of the particles, electrons, came from a single magnetic field, increasing quickly with time. Energy achieved by particle accelerator increased at nearly an exponential rate. After the cyclotron and the Betatron, they were followed by the electron synchrotron in 1947, the synchrocyclotron in 1947, and the proton synchrotron in 1952. In 1952, Courant, Livingston, and Snyder at Brookhaven National Laboratory proposed a strong or alternating gradient focusing that completely changed the present design for magnets. Magnets in vacuum chambers could be made far smaller with huge saving in cost and size. Currently, around the world, there are in operation as many as 30,000 particle accelerators. You can see here the number of units as a function of the activities. Only 0.3% of them are large accelerators, typically with beams of the order 1 GeV, for particle physics or synchrotron light sources for the study of condensed matter physics. Most of other applications require smaller particle accelerators. The growth of the energy of the particle accelerator has been quite impressive. The energy of a particle accelerator is plotted here in terms of the equivalent laboratory energy of the collisions with particles at rest. The Livingston plot is showing the exponential progress of the logarithm of the laboratory energy from 1930 until today. You can see that it covers about 12 orders of magnitude in significance. And the colliders, lepton hadron collider, are of course the ultimate form of collisions. Progress is measured for the accelerator with high energies, new technologies, and great ideas. From accelerator to collider, two methods have been used for particle physics experiment. Fixed target. A beam of particle, the projectiles, is accelerated and as a collision partner in a stationary target is used in a beam path. Collider, two beams of particle accelerated and the beams are directly against each other, so that particles may collide while flying in opposite direction. A collider setup is harder to construct and to operate, but it has the great advantage that according to special relativity, it speeds at speed near the speed of light. The energy of a collision between two particle beams hitting each other is far more effective than with a fixed target arrangement. The practical idea of a collider received serious consideration in Germany by Rolf Widerøe and others already in the 40s. Widerøe published the idea of a German patent in 1943. You can see here the original colliders patent by Widerøe, the 8th of September 1943. You can ask yourself, why did he write the patent? The answer he gave to me was very simple. Because at that time, that's the only way you could communicate realistically with people, because of the presence of the density or the problems of the middle of the war. The first electron-positron colliders are being described next. For a stationary target, the beam energy, the energy in the center of mass is the square root of twice the energy times the mass of the electrons. In a more effective colliding beam setup, two accelerated beams, each of energy E, are direct against each other, and in case we have the energy in the center of mass is twice the energy of each of the beams. The gain ratio, therefore, is the square root of the ratio between the energy in the center of mass and the mass of the electron. The first colliding plus and minus were built in the early 1960s. ADA in Frascati, near Rome, and VEP in Novosibirsk, USSR. Here is the picture of the ADA, Anello di Accumulazione, at the NFN in Italy, 250 MeV, electron against 250 MeV positrons. The construction was finished in 1961, and May-June 1964, the luminosity was detected for the first time. The first hadron proton-proton collider, it's called intersecting storage ring, began at CERN in 1966. The collider was operational in 1971. You see here a picture of the CERN ISR. The radius of the ring was 150 meters, with 8 crossing points of the two counter-rotating proton beams at an angle of 15 degrees from each other. The highest center of mass energy has been 63 GeV. A stack of a DC current at up to 50 amps had been stored with protons from the CERN PS. Novel accelerator-driven technology was another important aspect of the development. These discoveries were made possible by a number of novel and extraordinary technological developments, replacing the original bubble chambers invented by Donald Glaser, Nobel for Physics in 1960. The Nobel was awarded in 1992 to George Sharpak for his invention and development of particle detectors, in particular for a multi-wire proportional chamber. Photomultipliers, ultra-pure water Cherenkov counters, were developed for huge neutrino experiments in the USA, in Japan, the so-called Kamioke detectors of growing dimensions, and elsewhere, leading to several Nobel Prizes in physics. A new technology with ultra-pure part per trillion liquid argon and xenon time projection chambers started in Italy in 2010. With a 700-ton Icarus underground experiment, a free electron lifetime of many meters. Liquid argon TPC is nowadays the main neutrino technology being pursued in the US Fermilab, with a future ultimate underground mass of about more than 40,000 tons of liquid argon, 1,300 kilometers away from Fermilab, and fed by the Fermilab Accelerators. Let me show you here the difference between the bubble chamber, which you see here. A Gargamel bubble chamber is an example. 40 bar pressure, pulsed, and duration 1 millisecond. And the time projection chamber, which you can see on the other side, no overpressure, continuously operated. The bubble dimensions in the two systems are rather similar. However, the sensitive mass can be was 3 tons in the case of Gargamel, was many kilotons in the case of time projection chamber. As I said, it is foreseen to go up to 40,000 kilotons. The liquid argon is a cheap used material, 1 franc, Swiss francs per liter, vastly produced by industry. The huge mega project at large distances are indicated here. You can see here the case of the Dune experiment. which is total volume in the United States, total volume of 40 kilotons, sensitive volume, and on the other hand, the hyper Kamiokande, which was discussed already yesterday, where purified water is used with a total volume of 1 megaton and fiducial volume about 56 megatons with photomultipliers, as many as 99,000 multipliers or 20 inches each, with covering 20% of the surface. These two experiments will be excellent facilities to discover most of the neutrino oscillation parameters in terms of statistics and matter effects, mass hierarchy, CP violation, precision determination of delta M31, and sin squared 2,3, proton decay, and supernova will be searched. New colliders at CERN, LEP and LHC. Following the observation of the W and Z boson and the discovery at the top, the SPS and at Fermilab PP bar colliders, a new 27-kilometer accelerator complex has been built underground, both over France and Switzerland, in order to realize a huge program with 4 main LEP electron-positron experiment, Aleph, Delphi, L3, Opal, and later 2 main proton-proton experiment, Atlas CMS, at a 7 Tesla superconducting hadron LHC. The main numbers of collected events have been as follows: LEP 1, 1989-1995, with 4.5 million Z0 events per each experiment. LEP 2, 1996-2000, with 10,000 WW events per experiment. There were 4 experiments, let me remind you. LHC, 2009 until today, is continuing. A new particle has been observed at 125.5 GeV in agreement with the X predictions. Today's accelerator complex at CERN, it's a very complicated and messy system, and you can see it here, how many things can be done. It speaks by itself. The LHC is indicated here. The huge dimensions of the tunnel are evident for the tiny curvature. You can see how small the curvature is to go around. Think how long it takes to get around 360 degrees at that rate. Thousands of physicists have contributed to LEP. Here we can see one example is Jack Steinberg, in charge of the Aleph experiment. Here you can see, sorry, it doesn't work. Here you can see Sam Ting, which should be here today, tomorrow, with in charge of L3 experiments with myself and George Sharpak, which got the Nobel Prize in Physics in 1992. Here they are, the two things, 1, 2, 3. Finally, Herwig Schopper and myself, the CERN director during the construction of LEP, at the day of the first successful collisions. You can see here Herwig Schopper, and my picture is there. Let me now go to the remarkable theory of Glashow, Weinberg, and Salam. Following the publication of symmetry breaking papers by Peter Higgs and François Elgert, in 1964, Severs Weinberg and Abdul Salam applied the theory mechanism to a model of electroweak symmetry breaking for the interaction between scalar boson and electroweak symmetry theory. For his achievement in 1979, Glashow, Salam, and Weinberg were jointly awarded the Nobel Prize in Physics for their contribution to the theory of the unified weak and interaction between elementary particles, including inter alia the prediction of the weak and neutral currents. The theory, and also the Nobel Prize, anticipate also the existence of a new massive neutral scalar particle, the Higgs, at that time, of course, still to be detected experimentally. 2 fundamental developments took place in the early 70s after the formulation of the Glashow-Weinberg-Salam theory. The first theoretical and the second experimental. On the theory, Feldman and Toft, which is here today, in 1971 described the GWS model, a gauge in which has the property that in all ordered perturbation theory there were only a finite number of infinities that can be absorbed into the definition of the parameters. The theory might then be able to describe weak and electromagnetic interaction energy well beyond the accelerators, and maybe well above, all the way up to 10 to 19 GeV, the so-called Planck mass scale or the initial Big Bang. The Nobel Prize in Physics in 1999 was jointly awarded to Veltman and Toft for elucidating the quantum structure of the electroweak interaction in physics. The second question has been experimental. The experimental discovery of neutral current, this developed did not guarantee that the theory was necessarily true, as has always been the case. Experiments were required as the definite matter of confirmation. In 1973, the so-called neutral currents were discovered in neutrino reaction at CERN and promptly confirmed at Fermilab. Experimental observation in neutrino interaction proved that besides the then hypothetical weak interaction mediated by the charged boson W plus and W minus, there was also the need of a neutral weak partner. This was, no doubt, another Nobel Prize class experimental discovery, which, however, never recognized. In my view, mainly because of the early death of André Lagarigue, which was the inventor and the developer of Gargamel. Unexpected event, this has been an unexpected event which has changed the expectation. Neutrinos are seen to interact here at CERN in a 1,200 liters Freon bubble chamber Gargamel. A mu neutrino, the vertical going line, interact with an electron and leaves the volume. You can see neutrino mu plus electron going to neutrino mu plus electron. You can see from the picture here electrons produced in this line, becoming an electron shower and a neutrino which escape the line of the question. Observed at Aachen in 1973, this has been the first experimental evidence of a neutral current event. In the subsequent decade, the GWS theory became progressively more and more consistent with experiments. In 1983, the next major experimental step has been the discovery of the W and Z bosons with the PP bar collider at the CERN SPS and the UA1 and UA2 experiments. You can see here the example of a Z going to electron-positron, an example of a W going to an electron neutrino. Let me also tell you another important point, which I think is relevant. Theorists and experimentalists have been very close to each other in this period of time, and they've been here represented as joining at the Nobel ceremony. You can see here myself as Simon van der Meer to the left in the first row, receiving the prize, with the second row, Abdul Salam with the turban, Shelley Glashow there, and Steve Weinberg here today, celebrating the 1984 Nobel Prize ceremony. LEP, the next step after the PP bar collider. More detailed studies in the zero LEP have been the next essential phase with higher rates and much cleaner conditions. This curve was already shown this morning and shows, for instance, the example of the WW cross-section as predicted here by the theory. You can see the experimental data and joining the theoretical prediction. Here is a more complete example of the data for OPA showing how the demonstration was performed in a variety of large possible channels. Higher quantum mechanical correction will have anticipated also the discoveries both of the top quark and the Higgs scalar. You can see, go back here. You can see here, for instance, the mass of the top, LEP1, LEP2, the mass, available mass in yellow, and you can see the experimental discovery of Fermilab occurring at the end of the analysis coming from the theory. Here you can see the mass of the Higgs between 114 and 200 GeV, and you can see here the experiment discovered at CERN in 2012 of 125 to 137 GeV. So the early expected Higgs at CERN came in 2012. In 2012, the CMS and other experiment have promptly observed the now operational CERN LHC collider and narrow line high significance with the mass of 125 GeV, the so-called Higgs boson. Here are the numbers relative to the experiment. You can see the picture of the standard model Higgs, which is predicted to be 4.21 MeV. Observation has been performed in several decay modes, however, always in presence of very substantial backgrounds. Experimental energy resolution has been so far much wider than any conceivable intrinsic widths. However, so far, no experimental evidence for any new physics like for instance, SUSY energies. Here is represented the immense complexity, remarkable complexity of the Atlas detection CERN. You can see the small little object there to be a man compared in a scale of values of the detector itself. And here you can see the picture for Peter Higgs at CMS, and let me compare the enormity of these projects to what has happened at the beginning of my talk when Rutherford constructed the first laboratory to do those things. Predict the stability of the X sector. For the experimental value, that Trovic is beta stable, but with lifetime or longer than the age of the universe. Standard model will be valid without any physical the way to the mass scale. Thus, there might be only one standard model X and no need for a no-fail theorem, and no immediate necessity for SUSY and CH energy, as shown by this graph. Future alternatives to the LHC tunnel. A high-energy plus and minus collider, square root S 240 GeV, may be constructed with the already existing, or in the already existing LHC tunnel. A high operation efficiency would require two rings in the LHC tunnel. One, a low emittance collider storage ring, and two, a separate accelerator injecting electron and positron very frequently into the storage ring to top up the beams. The high-energy LHC is another possibility, which would collide two protons of 16.5 GeV circulating in the LHC tunnels and a new dipole of about 20 Tesla with the same bendy magnet configuration. The center of mass of this energy, of the order of 35 TeV, becomes comparable to the 40 TeV of the then cancelled LCC in the US. High energy may also be profited for SUSE searches. However, for instance, the detection rate 0, background remains too large. New alternatives are required with new accelerators. Comprehensive studies of the X selector may require another accelerator in a new site. Two main alternatives being considered: the A plus and minus collider, L equal 34, with huge dimensional cost, namely 100 km ring, 4 times LHC, but limited at square root of S of 300 GeV, thus missing many of the extra-long Higgs boson diagram. A linear collider, ILC, which was discussed very frequently this morning, I've went to square root of S 1 TeV at 50 kilometers. This is a major technological which need to be developed. Project will all vastly exceed LHC in cost and time schedule. However, I would like to present another alternative: mu plus mu minus rings. Mu plus and mu minus rings have much lower cost and a much more shorter time schedule, and may be easily fit within the existing site, for instance CERN or others, but requiring the R&D development of a huge compression phase space of mu beams with two potential main mu plus mu minus alternatives. As channel resonance with L 10 to the 32 the X mass in order to study decay branching ratio, and second, a high energy collider ring, event up to 1 TeV, L 10 to 34 to study all other Higgs projects in the scalar sector. The method behind this alternative is called ionization cooling. This method, called the EDX cooling, closely resembles synchrotron compression or relativistic electrons, with the multiple energy losses in a thin Z absorber substituting the synchron radiated lights. The main feature of this method is that it produces extremely fast cooling compared to the traditional method. This is a necessity for the muon case. Transverse method oscillation are cooled by target foils, typically a fraction of gram per square centimeter thick. An accelerating cavity is continuously replacing the longitudinal momentum. Unfortunately, for slow muon, the specific DDX loss is increasing with the decreasing momentum. In order to cool also longitudinally, chromaticity has to be introduced. A future muon collider for the big X resonance is shown here. Signal and background are shown evidently. You can see how clean the signals are and how small the backgrounds are, and how easy it is to measure such a thing with a great deal of precision. Many other applications of accelerators. This is my last conclusion. The giant research accelerators are Hadron Collider in Geneva, with its 7 kilometers, is only the tip of the iceberg. Besides discovering the secrets of the universe, accelerators can shrink a tumor, produce cleaner energy, spot suspicious cargo, make a better radial tire, clean up dirty drinking water, map a protein, study a nuclear explosion, design a new drug, making heat-resistant automotive cable, diagnose a disease, reduce the nuclear waste, detect art forgery, implant ions in a semiconductor, prospect for oil, date an archaeological find. medical and industrial market exceed $3.5 billion per year. They are growing at more than 10% annually. Digital electronics now depend on particle beam for ion implantation, creating $1.5 billion annual market for ion beam accelerators. All the products which are processed, treated, or inspected by particle beams represent a collective annual value of more than $500 billion. Accelerator for transmuting nuclear waste. The key challenge facing nuclear fuel is reducing the radiotoxicity and lifetime spent fuel. In the US alone, a reactor will generate as much as 100,000 tons of total spent fuel in their lifetime. The spent fuel for a light water reactor must last almost 1 billion years to match the initial toxicity. You can see the picture here in years and the number of the remaining toxicity. And the white line is a line of the natural uranium. Transmuting these isotopes to shorter-lived products will reduce the lifetime in less than 500 years. You can see the displacement. This is, by the way, was a product on which I've been operating, which was mentioned by Klassenegger a minute ago. Accelerator-driven supercritical system is ideally suited to burn the most problematic isotope in the spent fuel in a high-power proton accelerator to generate neutrons or dense material. Accelerator fusion energy. And a nuclear fusion is potentially a clean and safe energy to study to source. Two studies will approach the low pressure, high long confinement using magnetic field confinement, and short confinement using inertial confinement. Accelerator technology plays a key role in both. Accelerator for cleaner air and water. Accelerator for treating flue gas need 0.8 MeV beam and 1 megawatt total installed electron energy per 100 megawatts plant. To use the water treatment, the beam energy is less than 5 MeV, wind power ranging from 0.4 megawatts to small plant to 20 megawatts to large micro plants. Accelerator for medicine. Circular linear accelerator has been developed for clinical use in radiation therapy of tumors already since the 30s, with the aim of achieving the high radiation dose, the tumor as low as possible dose to the tissues. The treatment of tumor needs a radiation dosage of 60 gray, which is usually given daily fraction of 2. Developed country, for each million people, about 3,000 patients per year need treatment for cancer. Half of them are treated with surgery and the other half by ionizing radiation. About 2/3 of these patients can be cured, but a large number cannot be treated satisfactorily. The unintentional radiation reactions of the normal tissue adjacent to the tumor, however, very often lead to the death of the patient. New types of radiation, such as neutrons, negative pions, protons, heavy ions, are therefore being studied. Now, this is an example of a radiation-driven therapy in Germany, Heidelberg ion therapy. Pion-driven medical therapy in January 2016, there were 45 particle therapy facilities worldwide. This represents a total of more than 121 treatment rooms available to patients. HIMAC, heavy ion medical accelerator in Cuba, Japan, began 1994, followed by many additional compact accelerators. However, the issue is then whether how best use the surgery. Proton therapy is still controversial. For instance, in the case of prostate cancer, most commonly dedicated for proton beam therapy, a clinical study directly comparing the proton therapy, brachytherapy, and other treatment that has not shown additional clinical benefit with proton therapy. Let me conclude. Particles accelerators have been in the forefront of nuclear scientific discovery for more than half a century. The accelerator technology has progressed immensely, while the beam energy, luminosity, facility size, and cost have grown by several orders of magnitude. Essential contributions have expanded many different fields or applications. A quick glance shows that since 1930s, the energy achieved by particle accelerator have grown exponentially with time, with an increase by a factor of 10 every 7 years. These increases were always due to new ideas and development and use of new technology. As we look into the future, one thing is certain. As long as we continue to make use of new accelerate technology ideas, new particle accelerators will continue to unpack unique and fundamental properties in science and technology. Thank you.
You talked about the mu plus, mu minus accelerator, but what are the prospects for it actually getting built?
Within my lifetime, 0. And probably within the lifetime of many of us, 0. All I'm saying is that if you really want to do something, you have to study a Higgs particle, which is already discovered, in much cleaner and much higher rate conditions. And this you can do with an existing accelerator, provided you use muons instead of electrons, and provided you construct such a thing within something which can be a CERN or can be ISS or other things like that. Therefore, in my view, the simplest solution to get to the best understanding of the quality and the results of standard model is the one not of building this huge 100-kilometer collider, but rather to adapt within CERN or within a similar place, Fermilab, whichever you want, a detector which will use muon instead of electrons, because it's well known, being a scalar particle, two electrons colliding into a Higgs have a much smaller cross-section, 40,000 times smaller cross-section than the mu plus mu minus going to the system. So the system is possible with very small accelerators, very cheap and easy to build, relatively cheap and easy to build. However, it requires the development of a new technology, the technology of muon beams. Now, I have been spending myself during the early times a lot of time in developing cooling for antiprotons, together with van der Meer, which justified the result of the discovery of the W. Now, I am deeply convinced that muon cooling is much easier than antiproton cooling. And therefore, it would be possible to construct a small ring of some 30 meters, which would fit in this room, just to speak, which could collect low-energy pions, becoming low-energy muons, and demonstrate that with that you can cool those particles using radio frequency fields to recover the energy lost by a DDX loss. Now, if that thing is proven to work, then the construction of a second ring, which will be half of the size of the CERN PS, which will be able to produce the necessary energy to study mu plus, mu minuses colliding with each other, is certainly possible. And in my view, is something that can be done on a relatively short time scale with an existing accelerator in a given time. That does not exclude the possibility to go further into other dimensions, but the time scale of going to a machine which is 4 times, 5 times larger than, look at the case of CERN, they want to make a ring which covers the whole Lake of Geneva and goes, if you make an ILC, you have to go from Geneva to Lausanne, which is something which is probably may be possible, but will require a major step forward, while this thing could be done in parallel with the LHC construction. Thank you very much.